Hello, I'm gonna present today something that I did a few days ago, and yeah, for some students, and I thought it would be interesting to share it here as well. I'm gonna present about flood hazard mapping and evaluation of river impacts with Lidar, photogrammetry, and hydraulic modeling. So it's a bit based on my experience, mixing a bit of Lidar and photogrammetry and how this is applied in hydraulic modeling. So yeah. We are gonna go through these steps, and objective is get to know a bit LIDAR data and how they can be used in hydraulic simulation and photogrammetry and the same. So what it's LIDAR, it stands for light detection and ranging, and there are different types depending on platform used. For example, it could be like a total station, or in a plane, or in a satellite, or even drones nowadays. Airborne LiDAR is very used. They can be delivered as LAS or LAS formats. This is an example of a river bathymetry taken by an airborne LiDAR, 3 kilometers long and very, very dense cloud. It's one of the most effective and reliable means of terrain data collection. And yes, it's becoming the most used technique for generating digital elevation models. We can talk about red LiDAR or green LiDAR. The red does not penetrate the water, the green does. I think it's related to, we make this distinction with the color because I think it depends on the range of the light you are in the visible and even not visible spectrum, but I'm not quite sure. And yeah, what about LiDAR in Spain, we do have to cover areas. It's more and more common in most of European countries. And also we have flood maps that are available in the National Flood Zone Mapping System. In Norway as well, everything is going by red LiDAR, and as well more rivers and coastal areas are being measured with LiDAR. This is an example of measuring with LiDAR with a total station. High precision model 3D point cloud. And a bit of photogrammetry, we talk about the structure from motion. That is a photogrammetric method for creating three-dimensional topography model for overlapping from overlapping two-dimensional photographs taken from many different locations and orientations to reconstruct the photographed scene. And this is one example of how we applied it. We do use control points that are these red dots in the, although nowadays they are not used, not so necessary because the drone itself has a GPS, but before the ground control points were really useful. Then you take the drone, take many pictures, and then georeference the model with these control points that are measured with a GPS RTK. And this is all models we have been taking throughout the time. Used for site recognition, computed weighted area for calibration, generate DMs for hydraulic modeling. So how do we process the data? Just take the pictures, create the cloud, the DTM, and the orthophoto. And this is a very interesting project where we study the ice formations during winter. So we could take pictures at different time of the winter, and this will quantify the ice formation throughout the time. And then, once the ice breaks, it creates the ice run that impacts the bridge, and that's our big forces that, that was a very interesting combination of using photogrammetry for measuring these forces. In site inspection with drones, it's very interesting. For example, like in this valley where access was really difficult, so being able to have a look at least with the drone, is useful. And this is the model we created from the flight. At present, there are already drones with LIDAR technology to acquire terrain data, so they are pretty heavy, and they require a good pilot. But yeah, it's becoming more and more used. This is an example of a project that we worked in Trondheim for Hydroflex project, hydraulic modeling for environmental impact assessment. We wanted to study the impact caused by large flow fluctuations as consequence of hydropeaking operation. We use the term hydropeaking to refer to large flow fluctuations caused by turbine operation. And why is that? In this picture you can see the discharge throughout a month or so, and you can see there are very high fluctuations going from 0 to 100 cubic meter per second because they turn on and off the turbines depending on the needs of the energy system. Yeah, so that creates an impact in the river because the water. Yeah, so let's talk a bit about the system. This is a basic system for hydropower. So typically we will have a reservoir upstream, then a tunnel that is collecting the water, and down here we have the powerhouse. So this ridge in red is what we call bypass, and it's left with very little water. So I think in this case it had a minimum flow of 30-35 cubic meters per second, but most of the water is diverted to the tunnel to produce water. And this downstream part, these last 8 kilometers, suffer from like large fluctuations. So how do these fluctuations affect the fish? How can we quantify? So that's why we using hydraulic model. In this case, we did not have bathymetric lidar, so we had to make a puzzle from the river banks. We did have lidar because it's the terrestrial lidar, but then we have some previous bathymetry measured by some colleagues. Then we measure some bathymetry, and we made the total. So this is an example how we were measuring with an ADCP, acoustic Doppler current velocimeter. And yeah, finally this is how the modeling headgrass looked like. We did some calibrations to make some adjustments, and finally I think we got a pretty accurate model of the river. And this way, with this model, we could do different hydraulic simulations at different discharges and find the critical zone. So for example, here we could see there were more like problematic areas, and like this one, because when the flow goes down, this is left without water and with these pools, which we actually observed a fish. I actually took this picture. And the problem is that, okay, this happens if we bring the flow down to 35 cubic meters per second, but if we leave it at 50, maybe we don't have this big issue. So how can we, put the boundary or give some advice or about when are the higher risk happening? Yes. This is another example of a study of environmental impact. In this case, we did have bathymetric lidar, which facilitated the work with very accurate models. This is just examples of how we quantify these problematic areas, and also we gave some advice on how to do the turbine operation. This is a flood hazard protection studies, Lidar River in Norway, where when the water comes, the village is pretty much flooded, but they wanted to, or there were plans to channelize the river, but even though that might solve the problems with the flood, when channelizing a river, you are completely changing the environment, so completely change like the ecosystem of this river. How can we find a balance between flood protection and protecting river ecosystem? So that was the purpose of this study here. There is a paper published out there if you want to reach out, and yeah. So that's it. Thank you very much if you liked it, or if you have any questions, just leave it down in the comments. Bye bye.